This is the last hour of Physics 1c for November 22nd. We're now going to do this RL circuit problem. Then we're going to talk about LC circuits. And then that'll be all for today. Okay, so analyzing an RL circuit. A sensitive electronic device with a resistance of 175 ohms is to be connected to a source of EMF with negligible internal resistance by a switch. The device is designed to operate with a 36 milliamp current. So the current, I'm guessing this is probably going to be max current, is going to be 36 milliamps. But to avoid damage to the device, the current can rise to no more than 4.9 milliamps in the first 58 microseconds after the search is closed. So we don't want the current to get higher than 4.9 milliamps in the first 58 microseconds after the switch is closed. Okay, so I'll just write those over here. So let's write it like this. I at 58 microseconds needs to be less than, it says no more, so less than or equal to, I think that's less than or equal to, doesn't really matter for this problem, 4.9 milliamps. An inductor is therefore connected in series with this device, as in figure 30.11, which is probably this one, right? Yeah. So this is the bottom half of the circuit. That's what we're dealing with here. Uh-oh, what happened there? Okay, there we go. So we know that our circuit looks something like this. We've got a resistor, inductor, so RL, switch, EMF, like this. Okay. The switching question is S1. What is the required source EMF E? So we want to find what is E equal to in part A. In part B, it says what is the required inductance L? And finally, what is the RL time constant? So what is tau equal to? Okay. So let's write down the things that we know. We know that tau is equal to L over R. We know that the current is a function of time in our circuit, looks like this. Okay. Wait. It's R over L, right? Yeah, it's R over L. Okay. And we're given a bunch of other information here. So we can figure out some things pretty quickly here. To find the EMF, I think what we can say is the EMF needs to be equal to I max times R. So that's going to be 0.036 amps multiplied by 175 ohms. That's 6.3 amps, or volts. I'll just write down here that then E is equal to 6.3 volts. All right. Next, part B says to find L, the inductance L. I think that means we have to solve this to find L, because we know this right here is true. So we have the ability to solve for what L is. So let's isolate L out of our equation here. So we have I of t divided by I max equal to 1 minus e to the negative tr over L. We rearrange that like this. This. Okay, so here what I did was I basically just switched places. This one went to the left side, this one went to the right side, and then I wrote it like that. We have to take the natural log of both sides. So we'll just do like this, natural log of this whole thing. The natural log of the left-hand side is going to be natural log of 1 minus I of t divided by I max this is equal to negative TR divided by L. Our goal is to find L. That means we need to say that, let's see, L is equal to then negative TR divided by natural log of 1 minus I of t over I max. And then we just need to plug things in. Assuming I didn't make any mistakes, let's look at the algebra real quick. So I divided by I max, and then we did 1 minus this is equal to this. We did the log of both sides, so we get the log of this whole thing. The log of this is just negative TR over L. Multiply the L over here and divide this whole thing down here. I think we did it right. So this is equal to, the time we were told the value of t was 58 microseconds. So this is going to be 58 times 10 to the minus 6 seconds. So maybe I'll just... we were given that information. The resistance in our circuit was 175 ohms, also given in the problem. We divide that by the natural log of 1 minus I of t. So I at 58 microseconds is 4.9 milliamps. That's the maximum that we can let it be. So in the numerator, we'll have 4.9 times 10 to the minus 3 amps. And then we divide by I max, which was 36 milliamps. So we'll have 0.036 amp. So there we go, and this should be our inductance. It does have the units of ohms times seconds, which is nice. Does anyone have any questions? So I get an answer that is 0.069. So we'll just write it like that, and the answer would be henries, or we could write this as 0.069 millihenries. So what did we do in this problem? Let's go back through and say we were told that we have this device that's supposed to have this much current maximum, but we know that to avoid damage, the current can't rise any larger than 4.9 milliamps in the first 58 microseconds. So we figured out that if you put an inductor in series with the device, so by adding this inductor here, it smooths out the current so that as long as we have an inductor of this size, the current will not spike to this number in the first 58 microseconds. Does it all make sense? Does anyone have any questions? The millihenries? Oh, whoops. My bad. This would be 69 millihenries. Oops. Sorry. There we go. MH would be millihenries, so 69 times 10 to the negative 3 will give this. The last question was, what is the time constant? And tau is just equal to L over R. So if we take 0.069 henries and we divide by the resistance of the circuit, which is 175 ohms, then we get our time constant. So we take that. And I get 0.39 milliseconds, which would be 394 microseconds, and that's what our tau is. So that is an LR circuit problem. They're really similar to the type of circuit problems that you did before with the RC circuits. Just a little bit different. Okay, final thing to talk about today is the LC circuit. This one is a little bit different than the other two. Now, for our LC circuit, we're actually going to not necessarily need an EMF source. So our LC circuit is going to look like this. We're going to have a capacitor, that is going to start off with an initial charge. So like this side will be positive Q, this will be negative Q. We're going to connect it up in series with a switch to an inductor, L. And we're going to talk about what happens if we close the switch at t equal to 0. Okay? And we're just going to kind of talk through what happens here, piece by piece. Okay. So, in this situation right here, when we close the switch, what's going to happen is that charges are going to start to move off of this plate, right? And I'm gonna put this into like kind of 4 steps of what's going to happen here. The first step is just going to be this picture right here, okay? So we're going to start from this position where the left side of our plate has positive Q, the right side of the plate has negative Q, and we're connected up with our inductor here. And we're going to say in this piece right here, charge is at maximum, but the current flowing in the circuit is equal to 0, okay? Now, after some time has passed, the charge here, because of us closing the circuit, is going to make it so that current will tend to flow in this direction through our inductor. But in that process, the current flowing through the inductor is increasing, so the inductor is going to induce a back EMF, which is going to slow down the rate at which that occurs. But after some time has passed, eventually there will be no charge on this, so Q is going to be equal to 0, but there is going to be current flowing through our inductor. So we're going to say the current here is going to be equal to the maximum value. And we're going to be saying that it's flowing in this direction here. So that's our current. It's going that way. Now, normally, what would happen is that after all of the charge was gone right here, there would be no way for the current to continue to flow. But because the magnetic field that exists inside of here tends to prevent the current from decaying away, it's going to keep the current flowing in that direction. It's going to slowly decay the current. Eventually the current will drop to 0, and it will drop to 0 when this right plate is fully charged. So the next step here is going to be the polarity of the capacitor is now going to be positive Q on this side and negative Q on this side, and there will be no current flowing through our inductor. So I is equal to 0 now. Now what will happen is that this capacitor here is now fully charged up, and so it's going to drive charges back in the other direction to neutralize with this one right here, because after all, there's a connection here, right? So the next thing that's going to happen then is that, or the next interesting step will be when the charge on our capacitor is back to 0, either side is charged, and there's now a current flowing back in the other direction here. So now the current is flowing this way and back this way. And again, we'll say that that current is the maximum current, but now it's going to be negative Imax. So if we called this current positive, this current is now going to be negative. And then what's going to happen next? Well, the current is going to flow in this direction until it charges up this guy. And we repeat the whole process over again. So we refer to this as oscillations in an LC circuit. And we're going to try to figure out how long this takes. But I'll tell you right now that if we say that this occurs at time t equal to 0, this is going to be a periodic type of situation where after one period has passed, we're going to be back to the same position. So position 2 here is going to occur at t equal to 1/4 the period. This one will be at t equal to the period divided by 2. This one will be equal to 3t over 4, and then we're back to t again, right? So every quarter period, you go through a cycle of the capacitor is charged, and then uncharged, and then it reverses polarity, and then it's uncharged again, then we're back to the original polarity, back to 0, reverses charge, back to 0. You see what's going on here? You're basically trading electrical energy for magnetic energy in this process, because you start off with an electric field. Let's use red for this. Let's use blue, because that's the one that I didn't really use. You start off with an electric field here, right? Here, the electric field is 0. But we have a magnetic field. If the current's flowing this way, probably the magnetic field points this way. here we have no magnetic field, but the electric field is now this way, right? And in the final position right here, if the current's going that way, probably the magnetic field is this way. It depends on how the coils are situated, right? So you go from electrical energy to magnetic energy to electrical energy to magnetic energy, and so on and so forth. And the process just repeats itself. Very similar to the way that a pendulum works, right? A pendulum exchanges gravitational energy for kinetic energies that swing through the bottom, and then it switches back to potential energy, to kinetic energy, to potential energy, to kinetic energy, to potential energy. This goes from, you could call this potential energy if you want to. You could call this kinetic energy if you want to, because it involves the flow of charges. After all, there is no magnetic field if there is no current. So you go from potential energy, kinetic energy, potential energy, kinetic energy, potential energy, kinetic energy, and you just alternate back and forth, basically. We can see this on the circuit construction kit here. If I just click this button, does that get rid of everything? Nope. How do I get rid of stuff? How about if I do File New? There's gotta be a way to, like, just get rid of all the things, right? Like, click that, can I just delete them? How do you get them off the screen? Do you just, you know what we're gonna do? Because I just think it's easier to do. We'll just do that again. Download it again. Keep open. Okay. So now what we'll do is we will grab a capacitor. We will grab an inductor. We're going to need to charge this capacitor up, actually. There it is, it's charged. I'll decide later if I need to. Okay, so we've got a charged capacitor, right? Got an inductor. Now we just want to hook them up. That one to that one. We will put a switch in here as well. And just for symmetry reasons, I don't know why I care. Okay. There we go. Let us also grab a voltmeter. Put him right there. All right. So we can see that the voltage of our capacitor here is 9 volts. And now what we're going to do is we're going to see this oscillation occur kind of like, not really in real time, but we'll just leave those like they are. What's 50 times 0.1? 0.5? Or 5? Square root of 5 is like 2. This might be too fast. I don't really know. We'll see. Okay, so yeah, here we go. I'm going to close this, and you're going to observe exactly what I saw. We start off with a positive charge here, right? So you can kind of track what's happening by looking at this device. So 3, 2, 1. All right, there we go. Discharged, but this makes it keep flowing until it reverses the polarity of that. And then that discharges as well, but this keeps it flowing until that's fully charged. It holds as much charge as it possibly can, then it pushes the charges back in the other direction until they get to here, and they're full up in this direction, and then it pushes the charges back in that direction there. Now, this wouldn't work with just a capacitor, right? If you take this piece out, then the system would just discharge itself, right? Just to show you that, I guess, let's pause this. Let's discharge this. Let's remove this. Let's connect these up. Just to be clear, if I were to open the switch, charge this dude up. Okay, wait, why is it not getting charged? It charged earlier. Okay, oh, because it's paused. There we go. Charged up. Get it back on our circuit here. All right, what's going to happen now? Will that same thing we saw happen before happen? No, because when I close this now, this is just a normal circuit. Even though it has a small amount of inductance to it, it's not enough to keep the charges flowing back and forth like that. So if I close this, it just instantly discharges itself, right? But by having the inductor as part of the circuit, that allows the current to basically keep flowing even though it wants to stop flowing, right? Oops. That makes it so that it wants the current to keep flowing, right? And so as a result, you see the oscillations that occur. What on earth is that? Just get that out of the way. So those are the oscillations of an LC circuit. That's kind of cool. Can you see how this capacitor here is almost acting kind of like a spring for these electrons? Like a springboard? Maybe you use the word spring as a wrong way to say it. Maybe more like a trampoline. It's like the charges flow into it until they can't flow anymore, and then they get shoved back in the other direction until they can't shove anymore, and then they get shoved into the other side. And then they start to push back now because there's an electric potential, right, that pushes back. And normally that would stop, except the current has to keep flowing because this won't let it stop. So that's your LC circuit. I find this to be really fascinating. Now, in real circuits, here, we can also do this. What do you think that the current as a function of time is going to look like in this circuit? Yeah, this is like a mass on a spring, and this is like a spring. This is a spring. The electrons are the mass on a spring. And the electrons have mass, so they don't... Yeah, so they basically, they get... Yeah. What do you think that the current as a function of time looks like if I put this on here? What would your guess be? If I stick this on here and look at the current as a function of time, what's your guess as to what it's going to look like? It's going to look sinusoidal. That's exactly right. So we put it on here. We may need to zoom in a little bit to see this. I think we do need to zoom in just a little bit. You're going to get a perfect sine wave. Perfect sine wave. Okay. I wish I could make this a little bigger, but I can't. Same thing with the voltage. If we were to look at the voltage, it would similarly be doing the same kind of thing. Well, not between these 2 points, but between these 2 points it would. Voltage is also going to be sinusoidal. And you might notice something else here. If I can get these to sync up, they're kind of like different sizes, so maybe it doesn't work very well. Are these lined up? Yeah, they're kind of lined up if I do like that. What I was going to try to say is that when the current reaches 0, this is at a maximum. When the current reaches 0, the charge is at a maximum. When the current reaches a maximum, the charge is at 0, right? So let's see if we can get all those features from mathematics as well. We can see it on that. Let's see if we can get them for the math too. Did I close this? Apparently I did. Maybe it just crashed. Okay, so to understand these oscillations, here's what we're going to do. We're going to look at our circuit and do something similar to what we've done before, where we're going to draw a loop here. And we're going to write down negative Q over C minus L di dt is equal to 0. We're going to start from that equation and come up with the charge as a function of time in this system. This one's actually pretty easy to do compared to the one we did a second ago. So to do this, we have to realize that the current I is equal to the rate of change of the charge in the system. So di dt has to be equal to the second derivative of Q with respect to t. So this whole equation can be written as negative Q over C is equal to L times, instead of di dt, I'm going to write this as d2q dt2. And now I'm going to move the C down to here, the L down to here, sorry, so that it says negative 1 over LC multiplied by Q is equal to second derivative of Q with respect to time. And now we have this formula that has shown up in physics before. This shows up when you talk about simple harmonic motion, and when we saw in simple harmonic motion that we had, I'm just going to say compare this to, if you go back and reread about simple harmonic motion, which you probably had to do in this class, because I remember the very first lab manual homework we had, we talked about the frequency of an electron as it oscillated around a ring. through the axis of a ring. The equation for simple harmonic motion looks like this. It's negative m over k times x is equal to, oh no, that's not what it is. It's k over m. Negative k over m x is equal to d2x dt2, okay? Where this system, what's going on is you've got a surface, you've got a spring with spring constant k, you've got a mass m, and the mass is basically oscillating back and forth like this. And this is the relationship you get because, well, where does this relationship come from? It comes from the fact that kx, which is the force, has to be equal to mass times acceleration. Kind of very similar to this equation right here. Except instead of acceleration, we have the second derivative of q, which is the first derivative of the current. Anyway, what we did in this situation was we looked at this symbol sitting in front right here and we defined it as omega squared. So we're going to do the same thing here. We're going to say, off to the side here, we'll say let 1 over LC be equal to omega squared, so that our equation becomes negative omega squared q is equal to d2q dt2. And that means we're looking for a function who, when you take the second derivative of the function, you get the same function back multiplied by an omega. And the only function, well, there's lots of options. One is an exponential function to an q of t could be basically, it could be something like this, e to the negative I omega t, or it could be something like a, well, there could be an a here too. It could be something like a times the sine of, omega t, or something like a times the cosine of omega t. You can try any of these functions, this one, or this one, and they will all satisfy this relationship, okay? Normally what we choose to do though is we just use a cosine function or a sine function. So I'm going to say q of t has to be equal to whatever the maximum amount of charge is on the capacitor. Of course, q max, I'll just say over here, in our system is going to be, actually we'll just call it q max because there's no battery in this case, I forgot. All right, it's q max multiplied by cosine of omega t. And we can then of course write the current as a function of time to be negative I max times the sine of omega t. And this gives us a simple relationship that we can use, which is that the current, the maximum current in the circuit, is going to be equal to omega times q max. You can figure that out if you compare those two equations right there. All right, so this is a really helpful thing that you're going to need for some of your homework problems. And this is also very helpful. The frequency is just equal to 1 over the square root of L times C. That's really handy. So we can figure out the rate at which the charges are going to move in the circuit by just taking 1 divided by the square root of the inductance multiplied by the capacitance. All right, good. Running out of time, but yeah. So we can calculate the frequency here if we want to. And we can see if this is doing a very good job of this. So let's look at these. Oops, here we go, show value. So 50 henries and 0.1 farads, right? 50 henries and 0.1 farads. So what's omega? Omega would be 1 over the square root of 50 henry times 0.1 farads. Is it 0.1? 0.1 farads and 50 henries, yeah, okay. So can you all tell me what you get if you calculate that? What's omega equal to? So this is going to give us that omega is equal to about 0.5. About 0.447 is what you're going to get. But that's in radians per second, and that can often be a little bit confusing. We can convert it into period if we do 2 pi over omega, and we can convert it into frequency if we do omega over 2 pi. So omega over 2 pi would be this divided by 2 divided by pi. Oops, didn't do that quite right. This divide 2 divide pi equals, and then if we do 2, well then the inverse of that. So I got the period is 14 seconds. That doesn't sound right at all. And I got that the frequency was 0.07 seconds. 14 seconds. We can check that, right? So the claim is that it takes 14 seconds for one full cycle here, right? We can actually see the time here, right? So let's wait until it's at a minimum or a maximum, and let's see if it actually is 14 seconds, okay? So we're about to hit a maximum here. Right there. That was at 785. So what's 785 plus 14? That would be 799, right? We're getting there. Looks like it's going to work, actually. There we are, 799, right back to the top again, right? The next time would be at 812, so 799 plus 14, no, 813. So we're at half cycle. A full cycle should be at 812, 814, right? 813, I said, yeah, there it is. Seems like it works. What happens in this system if we decrease this? Okay, if I were to decrease this, what's going to happen to the angular speed? So if I make this instead of 50 henries, let's say that I make it 10 henries, what's going to happen to omega? It's going to get bigger or smaller. So if I let this one go to 10, what does omega become? Is it going to get bigger or smaller? I don't want the number. I want you to just think about mathematically what's happening. It's going to increase, right? So that claim is that if the inductor gets smaller, then the frequency increases, okay? So let's see if that's true. So let's just reset. Change inductance to 10. Now we expect it to be 1 over this times this square root. So this is actually pretty easy to do, right? 10 times 0.1 is 1 second. So 1 over the square root of run is 1. So we believe that the angular speed should be 1 second, right? If the angular speed is 1 second here, right, then the period is going to be exactly 2 pi, which is 6.28 seconds. And the frequency should be, well, also one per second. Oh, these are the wrong units, by the way. I'm sorry. This should be inverse seconds. My bad. The frequency and the angular frequency are both going to be 1. This should be something like 6.28. To get those numbers, all I did was I took 0.1 times 10, which is 1. 1 over the square root of that is 1. So we expect that we're going to get a time here of 6.28. And more importantly, physically, we expect these charges to basically oscillate on and off very quickly. Okay, this thing should become charged and uncharged every quarter period. So every quarter of a second. So this should be really fast here. Let's see if that's true. Well, nothing's going to happen until I charge this up, actually. But let's go ahead and charge it up. Play. Pause. Okay, then we'll split junction. Move that away. Split junction, move that away. Reconnect here, reconnect here. I don't really need this on here, do I, for now? All right, and let's see what happens. Now, let's discharge this as well. Click play. Let it get going. Yeah, it's going way faster now, right? It's going way faster now. All right, let's see if we can come up with a way of counting this. I believe this should be 6.28, the time that it takes. So let's look at when it reaches its maximum here. That is around 8:37. So now if we add 6 to that, I can't even do it fast enough. We're already there, 8:44. That's about right. Yeah. So it is about 6 seconds now. You can visibly see it's going a lot faster, right? We do this, it should slow down. And it does. And it should slow down, right? Because now there's more mass in the circuit, right? It's a lot heavier. Because if I increase this to 100, yeah, okay. So the last thing I want to mention is what happens if we add a resistor in here. But I want you all to predict what's going to happen before I do so. So let's change this back down to 10. Done. So now it's going to be oscillating pretty quickly here. Actually, for this, I think I might want to... Let's actually make it kind of slower. So let's go back to what we had before. Let's go to 50. And that's all we're going to change. So show value, charge this one up, play, pause, just delete this. Okay, so now you all tell me what's going to happen in this scenario if I add a resistor in here. What do you think? This is going to be the RLC circuit, which we're going to be talking about a lot in the next chapter. What's going to change now that I've added that resistor to my circuit? Previously, the energy of my system never changed, right? Because the maximum current didn't change, and the maximum charge didn't change. The voltage across the capacitor plate didn't change. The frequency is actually not going to be affected, which is kind of interesting, but something will be affected. With that resistor being there, and it doesn't even need to be a resistor, actually it could be a light bulb. In fact, let's make it a light bulb because I think that's going to be, that's actually going to be more useful to us to seeing what's happening here. You're going to lose energy. That's exactly right, Josh. Now what happens is that previously we were treating these as ideal objects, okay? In fact, if I click on this right here, you can see that the wire resistivity is set to 0 in the simulation. That means that the system can never actually lose energy. Well, that's actually not true. We're going to learn that through electromagnetic waves you could lose energy, but in the simulation, no energy is being lost. But by placing this object here, we allow a way for energy to escape the system in the form of, well, heat and light, right? So what's going to happen now is that the amplitude of the voltage, which is a direct measurement of how much energy is stored, is going to decrease over time. So let's see if we can observe that. So here we have this, looks like a sine wave, right? Looks like a sine wave. But what's happening now is the peak voltage now is only 5. And when we get to the other side of this, we're going to need to zoom in a little bit. Now the peak voltage is much less than 5, and on the other side of this here as well, keep zooming in because it's getting smaller and smaller. Now my peak voltage is like almost 1. Zoom in again for the next cycle, because now the peak voltage is going to get even smaller. Now the peak voltage is about a half. Zoom in for the next cycle. So can you see that the voltage is slowly trickling out of the system effectively? Here. Now it's at 0.25. On the other side now we're at negative 0.1, a little over 0.1. I'm zooming in here, but the current is basically going away. And you can see on the circuit, there's basically nothing left in there, right? And if we were to put this around here, whereas we started with 9 volts of energy, now we're down to a very small amount. So small that the simulation isn't even drawing the charges on here anymore. But the peak voltage is getting smaller and smaller and smaller. So if you want to look at what that looks like in general, if you have a circuit where you have a capacitor, an inductor, and a resistor, so we put all of our things together, the so-called RLC circuit, connect that up, start off with a bunch of charges on this dude. What this is going to look like if you plot really anything, current, voltage, whatever you want as a function of time. I think the easiest thing to do is to plot the voltage across the capacitor as a function of time. So if we plot the voltage across the capacitor as a function of time, now what it's going to look like is this. It'll start off at maximum charge, so maximum voltage, but then it will kind of slowly decay off, following an envelope kind of like this. Do my best to draw this like this. And the way that the curve is going to look, that's not the curve, sorry. This is what the curve is going to look like. It's going to be a sine wave inside of, it's like a decaying sine wave, basically. Like that. And this, of course, is because this object allows energy to get out of the system. Energy dissipated through this. Whereas these two objects, we treat them as if they don't really have resistance. Even though in reality, any of you that have worked with electrical circuits probably know, if you've worked with this kind of stuff, that capacitors actually have a little bit of resistance to them. Inductors have a little bit of resistance to them. And you can also say that some inductors actually have a certain amount of capacitance, and some capacitors have a certain amount of inductance. All of these three things they're very hard to separate from each other. And the reason for that is really simple. If you think about what an inductor is, right? What is an inductor? It's a bunch of coils, right? And if I tell you that I have an inductor and it has an inductance L, you would be very right to ask the question, what is the resistance? Right? Because if it's a bunch of coils that are wound up like this, that's actually how we create resistors too. The difference is that when we make resistors, we usually make them to have these really, really, really tiny cross-sectional areas so that their A is small. And when their A is small, the area, that makes it so their inductance is small, right? So we call this thing a resistor and we call this thing an inductor, usually because the area here is big, whereas the area here is tiny. Okay, but nonetheless, any given resistor is probably going to have some amount of inductance, and any inductor is going to have some amount of resistance. There's no way you can get them. There's no way you can separate them, right? Because they're constructed out of the same kind of thing. And inductors are always made out of wires. So unless you construct an inductor out of superconducting wires, it's always going to have some resistance to it, right? But in this class, right, since we're learning about things from like a kind of very, very theoretical perspective, we tend to separate these objects away from each other. So we have a resistor, an inductor, and a capacitor that are all different things, basically. Yeah. I mean, now the capacitors are quite a bit different, right? Because it's these plates that have been rolled around. But if you really think about it, also the capacitors are wires that have been rolled around in circles, so they probably have some inductance to them as well. I think that in the engineering world, they refer to this as like parasitic resistance or parasitic capacitance, because it's a kind of resistance or capacitance that is like a parasite on your circuit design. But it's not like I know anything. I just learned that from watching videos on the internet. So what do those people know anyway? They don't have to have any kind of, credibility to publish things. They seem like they know what they're talking about. So regardless, the point is that in this class, though, we will treat these things as pure objects. We're not going to worry about the resistance of the inductor, the resistance of the capacitor and stuff like that. We're just going to treat them as these pure objects. And in the next chapter, we're going to discuss what happens when we connect these objects up to an alternating current, and we're going to find that they behave, not a lot, but in a different way whenever you put things into an alternating current circuit. Okay, we're out of time now. I went over a little bit. I'll stop right there. We do have an exam this week. It covers this chapter as well as the previous chapters that have come before. What I told people before was that it's basically the chapters 28 through 30. Is that right? Let me make sure. I think it's also 29. Definitely 28, because that wasn't on the last exam. But I may put problems from 27. So it's going to be chapter 27 through 30. Because I don't have to stop the thing right now. So exam 3, chapters 27 through 30. We did do a little bit of this stuff on the last exam. I'm just saying that this is still fair game for this exam, okay? So the topics of these chapters are magnetic force, source of magnetic fields, in case your book has different numbers or something like that. This is 27, this is 28. Chapter 29 is induction. And chapter 20, this is like Faraday's law, basically. And then chapter 30 is inductance. Right? And so this is basically RL circuits. RL and LC circuits. So it's RL and LC circuits. Circuits. Inductance. As well as the idea of self-induced EMF. There's a topic called mutual inductance, which is in this chapter. I'm not going to put that on the exam, but you may want to learn about it. All right, that's all I got. Any questions? I will stick around and answer them, but I'm just going to stop the video there.